So, how much is that force? And so I'll emphasize, maybe I'll move this out. This might block the video for some of the calculations if I go kind of low here. But I'm going to do exactly the same calculation. So let me put in the G, 6.67 times 10 to the negative 11. There's a Newton, there's a meter squared, there's a kilogram squared, okay? Then I need to put in the two masses. Now the first mass will still be that lead sphere. I'll say it again, need to do it in kilograms, so 1.5 kilograms. And the second object would be the mass of the Earth, because that's what I'm asking for. What is the force between it and the Earth? And the Earth is a very, very big object. It happens to have a mass of 5.98 times 10 to the 24th kilograms. We're out of time here for today, but when we continue this tomorrow, I'll show you how that is worked out. But then I need the distance between them. And here's where I want to draw a picture. Because if this is the Earth, and then I have a table, and then I have the lead sphere, and that lead sphere is about 1 meter, and catch this, it's 1 meter above the surface of the Earth. Is that 1 meter what I put right here? Yeah, good. I hope a lot of you are saying, no. What you said is that the distance between them is from the center to the center. Not from the center of the object to the surface of the Earth. It would have to be the distance all the way to the center of the Earth. And another useful number here is that the radius of the Earth is 6.37 million meters. And so when I say what is the distance between them, it would be 6.37 million meters. And I suppose if you want to say plus 1 meter, because it really is 1 meter above the ground here, I'll go with that. But in tomorrow's discussion, I'm going to begin to ask you, does it really matter if you add 1 meter versus 2 meters versus 3 meters? I mean, that's kind of small potatoes compared to this. And so let's continue with this discussion. But I'll, just to make it look correctly as we run out of time here, I'll add 1 meter. And then I will get out my calculator. All right. So in the numerator, I have 6.67 times 10 to the negative 11 times 1.5 for the mass of the sphere. Then the 5.98 times 10 to the 24. Then divide by 6.37 million meters plus 1. And then square that. And I get 14.7 newtons. And yeah, there's a lot to talk about in this problem, and that's where we'll pick up tomorrow. But I'll end here with just saying, do you see that this number, see, this is 10 to the minus 8. This is 10 to the 1. There's 9 zeros. This is 1 billion times bigger than that one. And so the amount of pull downward towards the Earth is 1 billion times more than the pull sideways. And that one's really hard to detect. But I'll call it quits here for today and just point out, I hope you got the beginning part of the universal law of gravity. The neat thing is it is universal. That's the one and only calculation. We put that together with chapters 1, 2, 3, and 4. And we can do some really neat things and talk about orbits and satellites and all kinds of things that we will tomorrow. So, see you tomorrow.